Okay, so today we'll spend most of the time on how to deal with missing data. So as we mentioned last time, I'm looking at this data set on a consumer expenditure survey. These are just some of the variables. There are like 500 variables, but not all of them turn out to be so important. So I highlight those, at least those that actually appear in the trees later on. So if you have this PDF, look at the trees. If you want to look at the definitions, you can refer back to these pages. But also in the last column, show the proportions of missing data in each of these variables. Some of them do not have missing data, like the first one, age of reference person, is 100% complete. Age of spouse, 41% missing. Federal income tax refund, 55% missing. Reason for not working during the past 12 months, 63% missing. And so, it goes on and on and on, and some of them are just, very, very large. So like 97% missing bracket range of bank accounts. You would think most people have bank accounts, but 97% of the data for that variable is missing. And the other two are also dealing with bank accounts. So you also see another feature here is that there's all kinds of multicollinearity, right? They ask you how much do you have in your bank account, then they ask you, in case you don't know, the next question may be, how about these ranges? Can you identify the range? So some people cannot tell exactly how much money they have, but they can identify a range. Some people can do both. Now, once you have both, you have correlations. And so some people are very afraid of multicollinearity, but you get lots of them. For example, this consumer expenditures, they will ask you how much you spend on food last year, how much you spend on transportation, entertainment, books, and so forth. And one question in the end is, what is the total expenditure? So they're all supposed to add up to that X11, right? So now, if they do the addition correctly, this is not only multicollinearity, this is strict linear dependence. The other thing that you see in this kind of data is that you get bracket ranges. Now, those bracket ranges are bracket ranges. They are not numbers, but they're coded as numbers. The first bracket range may be, first bracket is 1, second is 2, third is 3, and so forth. Now, if you want to do linear regression, do you treat those as 1, 2, 3? Now, do you treat the metrics, the numbers 1, 2, 3, that are equally spaced? Are they actually equally spaced? But those brackets are not really equally spaced. And people, what do you do? Really, what do you do? Do you try to change the distance of those numbers? Okay, if you do that, then you're putting in some information that is not in the data. It may be valid information, but it's not in the data. If you don't, then you are using some information that's just arbitrary because they just coded 1, 2, 3, right? So these are all kinds of problems that a regression tree method will not have. At least a piecewise constant tree method will not have, because if you have bracket ranges, and if the split is between the second and third brackets, well, it's between second and third brackets. You don't have to redefine what is the first bracket, what is the code for the first bracket. So it's a split between 2 and 3, then it's between 2 and 3. Brackets 2 and 3. If it's between 3 and 4, then it's between, all brackets up to 3 on one side and all the others. So there are a lot of headaches that just disappear. So when I teach undergraduate class, and I give a data set like that for the students to use, and they all, unconsciously just take the 1, 2, 3 as a real, measures. And then they get penalized, and then they realize, oh yeah, then they don't know what to do. I don't know what to do too for that, because if you change the spacing 1, 2, 3, so if you think that the distance between 2 and 3 is actually wider than the distance between 1 and 2, then you have 1, 2, and then jump to 4 instead of 1, 2, 3, 1, 2, 4, and 5 or maybe 10, right? But then now you're putting in some information which will change your parametric model for sure, right? And this is without talking about missing data. And of course, there's the other thing about top coding where you truncate, and then there's also censoring where you don't need to truncate, you just know that it's beyond some number, right? And we'll talk about that later. So back to here, so you see this now it's sort of like it's just like super horrifying, 99% missing. Okay, so most people will say, well, why do you want to use a variable that's 99% missing? Okay, I throw it away. What about 98%? Do you keep it? No, throw it away. Okay, what about 97%? So at what point, okay, at what point do you stop to throw away variables? Okay, and especially, you know, if the variables seem to be totally irrelevant, it's okay to throw them away. But these variables we are throwing away, they all pertain to an amount of interest and dividends, which is a y variable, right? So you don't have to throw away too much of that. And collinearity, some people will say, oh, I worry about collinearity, so I only use one, right? Or I use a principal component of all this bunch and just use one. But if you remember the example we had earlier on the car data, so let me just go back. Just want to mention that. Yeah, here. Now, the width of a car and the length of a car are collinear, right? The wider the car, the longer the car. Now, because they're collinear, you throw away one, so you throw away width, just use length. You miss this picture. It is precisely because of the relationship between length and width of a car that helps you separate the SUVs from the pickups. If you throw away one of them, you never get to here. Then you have a harder time saying that, well, okay, SUVs tend to be shorter than pickups, but not necessarily. They are longer SUVs, but they are proportionally wider too. You see, so it's a geometry of the car that requires you to have length and width. Okay, so I wouldn't, you know, routinely throw away collinear variables. Basically, the thing is the following: we are in a classification situation here. If you're not in a classification situation, then principal components will work fine. So I always tell students the difference is, if you use principal components, there are no colors. If there are no colors, if all the dots are black and no symbols, only one symbol, then you can throw away one or you just use the principal component. But if there are colors, you should not use PCA, you should use LDA. And I'm surprised, you know, a lot of times, even when I go to conferences and, well, you know, respectable people, they use PCA when they have a classification problem. And they should not be using PCA, right? Okay, so let me go back to here. Oh, yeah, so this missing value codes. So here, this example is also unique in the sense that we don't have only one missing value code. We have multiple missing values, okay? Because the missing value comes with a reason. So if you think of an NA as a code for missing value, there's an NA sub A for this kind of missing valid non-response. There's an NA sub B for missingness because it's an invalid response, a non-response, NA sub C. So Guide can actually handle situations where you can have multiple missing value codes. They are missing because there's no number for it. But in government surveys, they often know why there's no number. Okay, usually it's maybe because it's an administrative thing. So like the person has no spouse, so it's missing. And the interviewer knows that, right? And the government has, over the years, because they keep doing this kind of surveys, they know about this and they collect that information. Of course, you can say that, oh, I can figure out that this person has no spouse because maybe there's a marital status, right? That may be a marital status variable, and I can look back up there. That's fine because we know about this data. But if this is a microarray kind of data, genetic data, you know, they're all gene expressions. How do you know that this gene, right, 20 spaces away is related to that? And only if this is possible do you have a value. You know, you don't know that. Okay. So just for interest sake, okay, we always think that if you have more stocks, you have more interest, right? So we think that stock is a good predictor. Amount of stocks you own is a good predictor of how much interest you get. Now, I show you this picture. We have 4,600 plus responses, but only 6% of these respondents have both values for Y and this X. My Y is the interest and dividends. This X is my amount of stock. Only 6% of them have these two values. So when I plot this to show you, I'm not showing you 100% of the data because 94% of the data cannot be plotted. 94% of the points are either missing the X coordinate or Y coordinate, right? So that's why in a way, plots are actually very deceptive. You know, a lot of students use R, and whenever they have data they plot, the trouble with R is in many other situations, R will give you a warning if there's something strange. But when you do a plot and there are missing values, R will not give you a warning. I will just plot those that are complete in X and Y. And you will never know that you're only seeing a subset of data, right? So here we're only seeing 6% of the data. But even then, it's very interesting. It looks like of this 6%, most of people have less than $1 million, right? 10 to the 6, right? There are 2 people with more than $6 million in stocks. But see how much interest and dividends they got last year. Almost zero. Almost zero. So what are these stocks? Are they losing a lot of money? Did they lose a lot of money that year? Or yeah, maybe these stocks don't pay interest. They're capital gains stocks, right? So it's really hard to do imputation here because the relationship is not very strong. So anyway, I did missing. So the red line is I just fit the dotted line, the black dotted line is just with the 6%. Then I also imputed the stock with 0, right? Because some people will think, well, if the person doesn't say he has, what is this amount of stock? Maybe he has no stocks. Maybe that's valid, right? So I imputed everybody with a missing value in stocks. And then, of course, then I'll have plenty more points, right? But rather than overlay those points, I just redraw the regression line. The regression line doesn't change too much, right? It changes a little bit. It tilts a little bit because we are imputing all the missing values in stock to 0, right? So it may not be totally wrong to impute the missing values for stocks to be 0, but then we are imputing 94% of the data. If you're imputing 2 or 3%, you say, okay, I impute with 0. But now you impute with 0, 94% stock is here. Right? 94% of them are missing. If you impute them with 0, suddenly now they're not missing, but all zeros. That may be, I don't know, you wonder whether how sensitive is that assumption that if they don't report the stock amount, then it's 0. Okay. Anyway, so now how does Guide deal with these problems? The first thing is how does Guide, so Guide has a split on the node, right? So suppose now Guide is checking on stock as X1 to split. So Guide uses a chi-square table, right? This is where Guide differs from all other methods, even those that use chi-square tables. Guide includes new columns for the missing values. All other methods that use this kind of chi-square procedure to do variable selection will only use those, will only count those data points that are non-missing the rows and columns. They just throw away those that are missing. Okay. What is the problem with that? The first problem is that when you go from chi-square table to chi-square table, the sample size changes. Those that have 94% missing, those tables only use 6% of the data. Those tables that have nothing missing use 100% of the data. Okay, so the sample size changes. When the sample size changes, we already said that the chi-square convergence is non-uniform. When the sample size changes so much, right, that makes the non-uniform convergence of the chi-square distribution even worse. So what Guide does is Guide uses 100% of data in every table. If they are missing, like here, Guide adds 2 columns. These are the NAs, but there are 2 types of NAs for stock. A is validly missing, presumably because they have no stocks. C is refuse to tell. Okay, the respondent says, can I not tell you? And you're allowed to say, yeah, okay. But then the interviewer will code it as a C. That means this person refused to tell, right? Or the person can say that, so for age of spouse, for example, I'm not married, and so age of spouse is NA, coded as NA, but then there's an A for this reason, right? So you see now, this is how guide deals with it. And you can see from here, actually, that for people with stocks less than 18,000, it's a 3 to 80 proportion for those above or below the mean. So just a reminder, the way guide goes from classification to regression, it has to get a chi-square table. In classification, the rows are like the type of car, SUV, wagon, pickup, and so forth. In guide, we fit a model. Here, we just fit a constant. And look at the positive and negative residuals. That is like above the mean and below the mean. So you see the two rows. Okay. The interest and dividends, the Y value above the Y bar and below Y bar. Right. So the positive and negative residuals. So you see, this is a 3 to 80. This is like 1 to 7. Now this reverse to 5 to 3. And then you look at this. This is pretty big, right? So there is some information in that A, in that missing value for A. It's not randomly missing. Okay. And if you throw that away, you throw away 2,300 observations there. It's really a lot of data. Okay. So for age of reference person, there is no missing data. So we don't have to add any columns. If there are missing data, we add columns, right? So this is how guide does variable selection, okay? And this is why, although nobody had asked, sometimes when I teach a class like that, some people ask, why do you use chi-square tables? You lose information, right? I discretize my age. My age is actually a continuous variable. I actually have an actual age for each person, right? So if you consider the Y here as 0, 1, because it's binary, you can do a linear correlation coefficient. Look at the relationship. Then I don't have to discretize, I actually use the real age, right? But if I do that, then I cannot handle missing data. But once I discretize, I have columns. Then I can always add a column for missing values, right? The other thing is linear correlation is only linear correlation. Right? You can have two variables that are like parabolic. They're not linear correlation. You just calculate correlation is 0. You think they are not correlated, but actually it's decreasing and then increasing. Right? But if you cut into groups, you can actually see in a very coarse way, right? So that's another reason why I decided, after many years, I decided to use chi-square tables. Initially, I actually used the analysis variance F test. So you could look at associations between age and interest and dividends by looking at it as a two-sample problem, right? Those with above average amount of interest and dividends, and those below average, and look at the age distributions, right? That's a two-sample t-test. Okay, so you can use a two-sample t-statistic to do that. Okay. And so I used that for a while in earlier iterations until I had to really think seriously about missing data. Right? Before that, when I think of it as two-sample t-test, I just throw away the missing data. Just do the t-sample t-test, get the p-value based on the non-missing data. Right? Okay, so that's what I do for that. Now, then there's second step is split set selection. You have to find the cut point. The first step there is find the x. All right. After you find the x, then what is the cut on x that you split the data? So suppose the first split is on stock. Okay, it turns out that it's on stock because if you look here, oops. The Wilson-Hill-30 approximation, I got chi-square. The two tables have different degrees of freedom. I converted it to a chi-square 1. So age is pretty significant, and you can imagine, right? I mean, if you are 18-year-old, you're not going to have $1 million in stocks. you may have to wait until your 60s or so forth before you have money invested. So age is a good predictor. But of course, the amount of stocks you have should be a good predictor, because that's, at least for some people, that generates the interest and dividends, right? So between the two, the 165 for stock beats the 108 for age. And so guide will split on stock. But when you split on stock, where is the cut point? People who only cursorily read guide will say that, oh, I've seen people say that, guide is not very good because guide splits only on the quartiles. That's not true. These quartiles or quantiles are used to construct the table. Once you choose the X, guide will do a sweep to search for the best cut. So it will look at all the data along this X variable, stop, look at each point, look at each X, which is a midpoint between two observed values, okay? And then for each X, you have a left and right node. And within the right node, it fits a constant, the constant of the Y bar left and Y bar right, okay? And it computes the variance for the two. And it keeps moving to minimize the total variance of the two subnodes, right? But when there's missing data, what do? Many people will try to impute the missing data so that it becomes an ordinary observation, right? You may impute it with mean, for example, right? But I found that a better way is to leave it as its own entity. NA is its own entity. So we consider the first split is like this. All missing values go to one side, which in the case of stock, where 94% of the observations go to one side. 6% go to the other side. See how good is this, right? So 94% of the respondents go to one side. They're missing stock, but they're not missing Y. They have Y. So we can calculate Y variance for this group. Those who are not missing stock go to the other side. They also have a Y, right? Okay, so that's the first split we consider. Then we start considering splits like this, right? Start moving the X. Each time, put the NA on the same side as the left. And again, calculate how much is the variance reduction. Then we do it again, but now put the NA on the right. So we cover all the bases here, right? We cover all the bases without having to force a number, a constant, for the 94% of the data points that are missing stock. Okay. What happens if the variable is categorical? So suppose it's race. And I think gradually we will have more categories of race. But in the past, if you look at past data, if you're multiracial, you don't check a box. There's no box for you to check. You leave it out, right? So if you're multiracial or biracial, you'll be recorded as NA. Now you impute. These people are biracial. They are not whites or blacks or whatever. You impute, in Western countries, you impute with whites. So now all your biracial people become whites, right? Which means that you have really, altered your data. It's no longer the same as the population. So what happens in this case, if there is no biracial or whatever category, we create a new category called missing race. After all, you have a category called white. You have a category called black, a category called Asian, and so forth, right? You can also have a category of people from Mars, for example, right? Just, new race, right? And that's fine. There's no need to impute that, right? And then when you split on race, then it's just one of those groups, one of those racial groups. And then you can go to the left or right, just like a white or black or Asian, right? Okay, so this is how, and this is the tree. Okay, so guys, splits first on stock. You see the splits, the conditions are, some are red and some are not red. The red are those with missing values. So I try to make these pictures as much standalone as possible. So this first split says that if stock is less than or equal to basically $500,000, 583,000, right? You go to the left. Where do missing values go? If the missing values go to the left, I put an asterisk under the inequality. So you can see over here, there's no asterisk. That means the missing value go to the right. So if you see an asterisk under the inequality sign, you will know that if you're trying to use this to predict for an unseen case, a new case, right? At the root node, if that new case is missing on stop, it should go to the left, right? So this is now very transparent. People want models to be transparent. In other algorithms, you may have heard of algorithms that use surrogate splits. Surrogate splits are like, if I don't have stock, I use the best predictor for stock. If x1 is missing, x1 is the variable to be split. The best surrogate split for x1, the best predictor is x3, for example, right? But x3 may also be missing. If x3 is missing, the best predictor for x1 may be x10. So there's a hierarchy. Now, if you try to predict a new observation, you can't tell actually where that new observation will go if it's missing x1, because you have to know what is the value of this first surrogate and whether that value is missing or not. If that also is missing, you look at the next surrogate. Even if that is not missing, the first surrogate is not missing, you must know what is its value and how does it work as a surrogate split. That is very hard to put in the picture, right? So others are worse. There are algorithms that, you know what they do? If something is missing, they randomly assign. Okay, statistically, maybe it makes sense, okay? Because you don't know why it's missing, you just toss a coin, right? After all, in statistics, we use random numbers very often. But if you randomly assign, you can never tell. When you use the models to predict a new observation, where it goes, it's random. You see? So see, I've been struggling with all this kind of things for years. And so I reach a point now that this is what I have. Okay. And of course, the taste is, what do you call that? The proof of the pudding is in the tasting, right? So the proof of the pudding is actually when you do cross-validation and see how the accuracy, and I have those results later on. And the accuracy is pretty good. It's not going to be super high, but if I were in a race horse and I know nothing else, I put in guided as one of my, I will not lose all my money. Okay, I may not win the grand prize. Okay, but on the flip side, if I was considering a new algorithm, if my student would come up with a new algorithm for the thesis, I'll tell the student, compare with guide. If you lose to guide, then it's not worth publishing. So in other words, guide is a good enough benchmark. Right? Don't use CART. CART has been shown to be very lousy, even in prediction accuracy. Right? So, but people still use CART, which is 1984. Now it's 2022, almost 40 years old. You don't compare a cell phone with a 40-year-old cell phone and say that, well, I beat that cell phone. But you still see papers published like that. They use RPAT, which is based on 38 years old ideas. And they beat CART. There's no big deal. They all beat CART. And referees who don't know will say, okay, yeah, publish. Right? So if you really want to show that you can beat a decision tree, you should include guide. Of course, if I'm the referee, I don't want to say that because they will know who is the referee. Okay, so I would just say, as a referee, I'll just say they should use some more modern algorithms. Okay, so if you just want to look at history a little bit, it says if the amount of stock is less than 583,000 or is missing, go to the left. Otherwise, go to the right. There are only 31 people on the right side. Okay, underneath each node are two numbers, one in italics. The number in italics is the sample size. The number below is the Y bar for that node. Right? So the 31 people, they have reported their stocks, and they reported their stocks to be above 583,000. On average, the amount of interest and dividends they had last year was 47,000 740. That's the number below the italics. Okay. If you go to the left, these are people who didn't have so much stock, although $500,000 is still quite a lot of money, or who did not report the stock. Then the next question is rent equivalent. That's a question that says, how much would your house be worth if you were renting it out now? How much would you charge for rent? Okay, so that's a measure of the value of the house. And if it's low or missing, then you go to the left. That's $3,947 or less. Otherwise, you go to the right. Okay, if you go to the right, then it depends on which state you're from. Okay, here the set of states is so big because there are like 50 states in the United States. I didn't want to print it into the picture. If you actually do the LaTeX on the LaTeX code that guide produces, it will have a caption at the bottom, and it will tell you what are those states that go left and right. But so basically, where you live will depend, will affect a lot. So if you are in this right group, you know, the amount of interest and dividend is 64,000. Okay, even higher than this group that have a lot of stock. Okay, so these are people on the right here. There are people whose house, if they rent out, they can maybe get a lot of rents. That's how they go to the right. So they must have a big house, right? If you have a big house, maybe a mansion, then maybe you're very rich. So, you know, it's related, right? But if you live in, maybe the people here are mostly in California or those rich states, right? If you live in some poor states, you won't be ending up on the note on the right, right? You may end up here, which is only 5,000, and here only 2,000, right? So, and then otherwise it's how old you are. Okay, so these are people who don't have a huge amount of stocks, whose homes cannot be rented out for a huge amount of money, and they are not very old. They're less than or equal to 53 years old, and they're like many of you guys except me here. I estimate you have no more than $1,398 in stock on average. Okay, right? Because these are young, relatively young. They're less than 53 years old. If you're older than that, then other things come in. So, you know, so this is the regression tree for predicting interest and dividends. Okay, so, and I color code them. You notice some nodes are yellow, some are red, some are blue. I colored them so that if the nodes are yellow, they're above the grand mean for the entire sample. If they're blue, they're below. Okay, but of course, it's not enough to just look how many more yellows there are than blues, because the sample size matters, right? For example, this group has a big amount of data, 1,100, right? We have only about a little bit more than that in the data set. So about 40% of data go right into that node. These are the younger people, right? Now this is the R part tree. It's not easy to see. So the first split is on FINCBT underscore X. The underscore stands for A. So it's actually income before tax. But the underscore means that this is a flag variable. Okay, so it's split on a flag variable. The flag variable equals to D. D means it's a correct answer. So yes, go to the left. Okay. So those people who gave, basically those people who gave an answer for how much was your income before tax, there are 90% of them that gave the answer. And their white bar is predicted to be just 1,822. Okay, so our part after pruning just stop there. There's no need to try to pass this node, even though it's a big node, because the action is in the other nodes where there are bigger variations. Okay, the variance in this node is very small. The mean is only $1,800. Okay, if you want to reduce variance, you are better off go for the part where there's larger variations in the interest and dividends than this one. And this is salary. And here is what I hate about our part. I don't know about you, but okay. It says if it's yes, you go left. That means everywhere, if it's yes, it goes left. That means salary bigger than this number, $213,000. Yes means go left. to me, the inequality left means less. You know what I'm talking about? You think of that inequality, right? You think that, you look at that inequality, you say, oh, bigger than equal. You think that bigger means go right. No, bigger means go left. So I don't know why the person who wrote this software couldn't just flip it around. Rather than force everybody. So like here, income rank, now it's okay. Yes means go left, right? This is okay, right? That is also okay. But sometimes it gets flipped around. So if you, see how do I center this? So for guide, I try to, this is actually just a coding thing, right? I mean, those of you who do coding, it's no big deal to make things, to help the user. So for guide, all the inequalities are pointing the same way. Yeah, it's all pointing the same way. So less than means left. Okay, greater than means right. You don't have to be switching around. Okay, so you see that in this R part 3, the stock variable never appears because it's missing 94% of the time. Because when R part considers the best at each node, he only uses the data that is complete in the Y and the X variable for that node. Okay, so when he considers splitting on stock X, it's only using 6% of the data. And you find that it cannot purify as much as if it uses variables with more data. Okay, so it never picks up anything that has a lot of missing values, which is okay if missingness is irrelevant. But if missingness is not irrelevant, then you can still get a prediction, just that the tree may have to be deeper. So in other words, you can do things early, right? But after a few levels, now you do serious work. Then you can recover the accuracy, right? So as far as accuracy is concerned, and that's why our part has survived for so many years. Now it's almost 40 years, right? Or more than 30 years, certainly. It's because people use it not to interpret the results, especially in computer science. They use it as a horse race to look at prediction accuracy. They do leave out samples, they do test samples and so forth. And our part, if you give it enough data, it will give you a fairly decent performance, not tops, but decent. That's because it can do stupid things. And after all the stupid variables are exhausted, now it does the real thing. It's almost like I have a gigabyte of data, right? I randomly divide into 10 parts. It's like I randomly split into 10. Now I do serious work on 1/10 of a gigabyte each time, right? Okay, so you can still recover your accuracy, right? The problem is when you try to interpret the tree, you can be totally misled because of this selection bias. Okay, so let me say something about how we want to estimate the population mean. So the original purpose of this project that the Bureau wanted to know, they wanted to estimate what is the population mean of this variable, interest and dividends, right? So let me with the population mean. That's the mean we're trying to estimate. Now, the data consists of two sets, the non-missing and the missing, right? If all of them are non-missing, I just take the average or weighted mean of the Y. I don't need to deal with the X's, right? Whether or not the X's can predict the Y, if I have all complete Y, I can just stay with the X's rather than try to fit a model to the Y's on the X's. But when some of the Y's are missing, I want to salvage them, okay? So I hope that maybe the X information in that set where Y is missing can somehow get me better accuracy, prediction accuracy on Y. So to do this, there is this well-known method called inverse probability weighted method, right? You basically take the weight. First of all, there's a weight variable I should tell you, because this is a national survey. Okay, they do cluster sampling. So I think each big unit, primary sampling unit is like a big city, like Chicago is a primary sampling unit. San Francisco is one, okay? And then of course, Madison, Wisconsin, where I live, is also one, but it's a smaller city. So the chance that Madison is selected is smaller than the chances of Chicago is selected. So there are weights, right? So when we, and the weights are defined by the government. So it's not something you need to estimate. So the WI. But what the inverse probability weighted estimate does is it divides by an estimate of the probability. So if you ignore the pi's, then it's just a weighted sum, a weighted mean, right? What it does here is it adjusts for the probability that something is missing. So for example, if somebody we manage to get him, and that person, we estimate the probability that he's going to be available is 10%. That means for everybody like him, we will not be able to, get access to 9 of those people. They will be maybe working late hours. We go there, he's not there, right? That's why we need people like him, people in his occupation and so forth, right? We only get them 10% of the time. That means that for everyone we get, there are 9 we wouldn't get. So you adjust for that by dividing by 0.1 to account for the people that you would have gotten if they were available. So that's how the inverse weighted probability estimate is. Then there's the other one. This doesn't really have a name. I just gave it a name, missing value estimation. Basically, I estimate, I get a y hat for the missing values. And then again, after I get that, then I just do a weighted average. Okay? So to use the first method, I don't need the observations that are missing the y, because this sum is only on S1. S1 is a set where y is not missing, right? But I need to estimate pi. And to estimate pi, I use all the data. Okay, so pi is the probability that the observation is not missing. So it's like a 0-1 binomial kind of situation, right? So now if I use the whole data set, I have a column that's interest and dividends. I replace that column with a 1 and 0 column. 1, if it's not missing, 0 is missing. Temporarily replace stop with this 0, 1. Now I do logistic regression to try to estimate the probability of y equals 1. This is what people normally do. They do logistic regression. The problem here is you cannot do logistic regression. One problem is that logistic regression, if you want to do multiple linear logistic regression, you need all the 500 x's to be not missing. And now you can see how crazy the situation is. All we're trying to do is estimate the mean of mu, which is y. If you follow this path, you have to estimate every one of these 500 other variables just to get back to you're only interested in the first column, right? But you have to move mountains to fill up the missing values in the other x columns. We have missing values in the y column, right? If we do something stupid, like just fill with the mean, we already have a job done and we go to sleep, right? But we think we can do better. Use logistic regression. Immediately you're faced with this problem. Logistic regression or linear regression, whatever, you need all the x values to be non-missing. And now you have to replace the missing values in x1, in x2, and so forth. For each replacement, you will fit a model of x1 on all the other x's. You need to fit a model. And you worry about model misspecification, because if the model is wrong, and you're fitting 500 models, eventually you impute all the x's, and now you take the imputed values as if they're real and fit another model to predict y. You can imagine how much work you've created for yourself, right? So anyway, that will be one way to do it, which will be very tedious. And those of you who have done logistic regression, you will know that in high dimensional space, logistic regression is an S-curve. You fit an S-curve, right? If you try to fit an S-curve, if all the y's are separated from all the ones are separated from all the zeros, that S-curve will converge to infinity. You have non-convergence. So you cannot really fit a logistic regression when they're separated like that. Of course, if you only have one x, you can see it. But in high dimensions, they can separate. It's called quasi-complete separation. It's not complete separation. They are not complete in terms of each xi alone. But in conjunction, it's like you have a waterfall, right? But the waterfall is not aligned to the boundaries of this room. The waterfall is oblique. Okay, and this happens very often when you have a lot of variables. So so even if you want to do something like that, you just cannot do it. So to use this method, you need to estimate pi, which should be like a classification problem, predicting 0, 1, right? Estimating the value of pi, which is probably the y is missing. If you use this method, then it's a regression problem because you are trying to estimate, get y hat for the group that is missing y using the x's, right? And so y is a continuous variable here. So instead of logistic regression, you can use linear regression. But you still have to impute all the x variables to do linear regression. So instead of, we don't have to replace the stock column with the 0, 1, just take it as stock. Okay, but now you only use the subset where stock is not missing. Right? If you estimate pi, use all the data because you need the zeros. You cannot only have the ones. Right? When the stock is non-missing, you have the ones. When stock is missing, you have the zeros. To do logistic regression, you must have some zeros. You cannot have all ones. Right? So to do the IPW method, you use all the data. If you use the second method, which we call the mean missing value estimation, MVE, use a subset where the y is not missing. Because there you don't replace them with 1, just take the actual values. Right? So that becomes a regression problem. So now if I do the first method, trying to estimate pi, this is the tree I get. So now I'm predicting the probability that interest and dividends is non-missing. Previously, my tree was predicting the y itself. Okay, so this tree can help me to get the y hat for filling up the missing values of y. But if I want to use the IPW method, if I want to use this method, I need to estimate pi hat, which is this one. But now you see the first split is response status is 1. This is like whether the survey was complete or not, some sort of flag. Okay, and then you see now something more something different comes out. The next split is this one. This is a missing value flag variable. This stands for retirement, survival, benefits, and so forth. So so basically RETS. I can go back to the definition. RETS, yeah, something like one of these two variables. It's a flag variable, okay? And they're 99% missing, okay? It's like how much do you receive in terms of retirement, survivor, or disability pensions during the past 12 months? And the reason it's 99% missing is there are not that many old people, right? To get survivor benefits, your spouse must have died, right? To get disability, yeah, you can be young, but most people are old, right? Retirement, of course, they're old. So that's the reason why it's 99% missing. So the first split, if you're trying to predict, so we're trying to predict whether y is missing. It depends, the second split here depends on whether this variable is missing, but not just missing. This variable is A. So it's not all missing values go there. Only those where the missing is because of a valid non-response go there. Otherwise, you go to the right. Okay, so and over here, this is federal income tax refund. How much refund do you get last year? If it's less than or equal to $7,000, or if the missing value for this variable is a valid non-response, then you go left. So Guide has this ability to separate out different reasons for missingness. It's not like, oh, if you're missing, you always either go left or right. No, some types of missing can go left. Some types of missing can go right. Okay, so Guide does this a little bit more meticulously. And all those red conditions are the flag variables, those that involve flags. So the black ones are those that involve the original variables. And again, the yellow colored nodes are those where the probability of missing is higher than average. The blue ones are lower than average. Okay, so this is what the R part tree does. Okay, so now I just give you the results. You can take a look at it. This is not cross-validation. This is too expensive to do cross-validation. I just apply all these methods on this same data set. If we use the weighted average of non-missing data, so I'm just lazy, right? You give me 4,600 observations, 1/3 of them missing. You ask me for what is the estimate of the population mean. I just take the 2/3 are non-missing. I take the weighted average according to the weights. And I get $4,697, right? So this is the estimate you get, the lazy estimate. Oh, am I? I'm out of time already. Okay, we'll end with this slide. $4,697, what you get as estimate for population mean if you just basically do nothing. If I use guide regression, I can use a tree or I can use a forest. Okay, this is IPW. That means I estimate a pi. Okay, I can estimate a pi using a single tree or I can use a forest. And the estimates become 4,557 for a tree, 4,786 for a forest. I use R part. Again, all these are IPW. Okay, IPW are here. Right? Right? So I can any algorithm that can do classification as well as regression, I can have two answers. So for R part doesn't have a forest, so I don't have anything in the second column. If I do use regression, so you see, when the column is 0, 1, most people will say logistic regression because it's binary, right? Actually, you can use least squares. Why don't people use linear regression for 0, 1 data traditionally? Why do you use logistic regression? Because they are worried that the white hat goes outside the bounds of 0, 1. That's why they use logistic regression. It's S-curve, it's asymptotes. You use a linear regression, you get a plane, right? But in the regression tree, the white hat is the mean of zeros and ones in every terminal node. So the white hat never gets outside 0, 1 because it's piecewise constant. So you can use linear regression in the basically you can use don't I call it linear regression? I call it least squares. You can use least squares as a loss function versus the binomial deviance. That's what logistic regression uses. Okay, so that's the answer. And now the MVW is where you estimate the white hat. So the bottom line here, which actually I think pleased the people at BLS, Bureau of Labor Statistics. I spent 2 summers doing this, and I think some people are a bit nervous that I'm going to, upset everything. At the end of that stay, I presented this. Everybody was smiling because it looks like it doesn't matter very much. Okay. I also have other methods that I don't talk about here, which the government has been using. They're about the same. Okay, at least for this data set. So this is about $4,500 plus or minus $500. So this is a little bit low, but so and there are other methods that cannot be used that I will talk about later. Okay, so again, I apologize for overshooting the time. So we'll see you next week, right? Oh, by the way, we will not use this room next week because there's an exam in here. We'll use MR13. This is MR12. I don't know whether 13 is next door. Okay, but I think Varun will put a note if you happen to come in. We forget you come and see a note and see nobody here. We'll be in MR13. Okay.